Okay, so today I'm going to be talking to you, as Leonie said, about a number of our quality trials over the years. Some of them are full scientific replicated trials. Others are trials where we had a suspicion how something might work and just taken a quick look to see how it has worked out. I'm only presenting data that is interesting. So where we got no results, I haven't brought that along. So just to set the scene, that's South African production up till 2018. As I understand, the 2019 year is a 60,000 tonne crop. So as you can see, there's been a fair amount of emphasis in South Africa, at least on increasing the overall value of the industry by increasing volumes. And certainly that is set to continue. That is the tree plantings or per hectare over the last 6 years. Just over 6,000 hectares in 2018. Again, I don't have the 2019 data for that. So we're in a situation of strong growth in terms of volumes, but in South Africa, there's also quite a premium attached to quality. We don't pay out every grower the same price for their crop. It is based on the quality to some extent as well. Just to give you an idea of how much quality can affect the price back to the grower, I've taken every processor every season puts out an offer letter, or what they're offering for the season, that sets out the base price and processing costs and the premium they'll pay for certain styles. So from the letters from 2018, I've drawn a few examples just to give you an idea of how the pricing works. So at the top of that graph, or top of that slide, you will see that for style 0, $20, that's US dollars, not Australian, $20.50 per kilogram for style 0. For the small styles, the broken stuff, $16.50, and for commercial or dark kernels, $12. So quite a big difference between the top and the bottom. There's also a sliding scale used by some processors, and I must say not all processors use the same formulas, so not all of this is relevant to one processor. Okay, you see some processors use a sliding scale where they pay based on sound kernel recovery. Over 42%, you're looking at about 100 Rand per kilogram grind shell. And for 16 to 17% recovery, 33 Rand, so only 1/3 of the top price. There's some penalties attached as well for unsound. If you deliver between 0 and 0.5% unsound kernel, there's a 4.80 per kilogram nut and shell processing cost. And if your unsound is over 9.5%, you're going to be paying 12.50 Rand. So definitely an incentive to send only better quality nuts to the factory. So what do we mean by quality? I'm just going to run through some of the basics that everybody knows. And these are the really obvious ones. You'll see at the top of that slide there's 4 kernels, each from one of our 4 main cultivars. And below that, one of the negative quality attributes, namely mold, kernel discoloration, pre-germination, some immature kernel, and insect damage. Those are the easy ones for the factory to sort out. When the kernel's on the line, they can be pulled out really easily. So we've discussed a number of price determinants and a number of the issues. Okay, let's just quickly run through this. So price determinants, I'm just going to summarize. Kernel recovery is one of them. There's sort of negative aspects like blemishes, mold, broken kernel, immature kernel. And there's some positives. If it's whole or whole larger kernel, there's a premium attached to that. We've done work on a number of these over the years, and what I'm going to be talking today about is the ones in red. Kernel recovery, blemishes, in particular, well, not in particular, only kernel discoloration, and that our form of discoloration is something I don't think you see quite so often. I'll show you a picture in a moment. Broken kernel, how can we reduce the amount of broken kernel? And yeah, how can we get more holes? So in terms of kernel recovery, we found over the years that the total kernel recovery certainly is affected by cultivar. In South Africa, it's affected by altitude. Our historical areas are all at around 700 meters above sea level, but the new areas are all at the coast, between 0 and 50 meters above sea level. And one of the clear differences is that at the coast, at sea level, there's a higher recovery for every cultivar. Regardless of the cultivar, it's the higher recovery at the post. Why altitude should affect it, I don't know. I don't think it's altitude per se. Plants don't really sense how high they are above sea level. But there's factors associated with sea level, like higher humidity, more moderate temperatures, certainly in our case, better rainfall during the development of the nuts. So that sort of combination is what's driving the difference. Okay, in orchard practice, I'm not going to say anything about orchard practices other than that things like irrigation and fertilization can play a role in kernel recovery. Okay, so the first trial I'm going to talk about today is about kernel recovery, but it's not a trial that was designed to look at kernel recovery. What we were doing was working with growth regulators to see if we could inhibit flush length on new flushes because of the regrowth we get after pruning. So we worked with a growth inhibitor, active ingredient uniconazole, trade name Sunny. It's used often in avocados. Are you aware of it in Australia? Yes, okay. So we use Sunny as a 1% foliar application, sprayed to runoff, and this was shortly after flowering and set. And we monitored the flushes through the next year, and nothing much happened. We didn't get any significant reduction in growth, but when we harvested the trial and started looking at the nuts, we saw something quite interesting. The trial involved 3 cultivars, Beaumont, 788 and 816. So for each of those cultivars, there's 2 lines, a control and a sprayed. And we've got Beaumont, that because the trial was sprayed, it's all those cultivars on one orchard, so the trial was sprayed at a particular date, one date. So the different cultivars were in slightly different stages of development. The Beaumonts were just past petal drop, just starting to set. 788s, the nuts had reached a diameter of around 6 to 8 millimeters, and in 816 they'd reached a diameter of 10 to 12. And the interesting thing that came out is for 788, a 36% increase in total kernel recovery. That's 788, and 816 a 21% increase. So the first question was, well, what's happening here? I mean, total kernel recovery refers to a ratio between shell and kernel. So the first question is, what's happening? Are we having an effect on the shell or on the kernel? So we cracked those nuts and had a look, and definitely the major difference was larger kernels in the treated trees. So yeah, that was an interesting result. It's not what we expected, not what we were looking for. The trial sort of ended there because the funding was for the growth, the vegetative growth aspect. And yeah, there's probably room for a lot more work there. Having said that, we got no growth control on that. I'm just going to throw in a quick slide that's got nothing to do with quality, but we did a few years later a trial on applications of uniconazole to the soil, which is a big practice in South America for avocados where it's highly effective. And what we noticed, okay, I've split it, let me just explain the pictures. On this side, I've taken flushes, cut them, removed the leaves. That was from tree or branches where only the terminal bud had broken. On this side was where the terminal bud and subtending buds had broken. So that's the one separation. The other separation is controls versus treated. Controls and treated, and the arrow indicates where the most recent flush broke. You can see with uniconazole a very reduced growth, and this is not the first flush after application, it's a year after application, so this is 2 or 3 flushes down the line, so it has a very long residual effect. So that seems promising, a soil application to reduce growth, but in this case too effective. If you look at these branches here, as I said, it was the second or third flush after application, so the previous flush had short internodes as for the most recent one. If you count how many leaves are sitting at those nodes, it's probably between 50 and 70. And the product also causes a slight increase in individual leaf sizes. So you get an extremely dense cluster of leaves in a very small area. It basically looks like a cabbage, which is not what we want when we work with growth inhibitors. Okay, so kernel breakage and how to prevent it. A lot of work has been done on this topic. Very good work done in Australia by Helen Wallace and David Walton. I'm not going to be talking about what they've done, you're probably aware of it. What I'm going to talk about today is some work we've done on the effect of the type of cracker used, cultivar, the interaction between cultivar and cracker, and some trials we've done on curing. Okay, so for the cracking trials, this is the data for Beaumont. You'll see we've used 3 cracking methods. One is hand cracking, one is a commercial shore cracker, and one is a commercial roller cracker. You'll see for Beaumont, the roller cracker produces a lot more small pieces than the other types. Hand cracking was the best for holes and holes, but that's not practical. For 816, the differences are not so good, not so great. All the cracking methods produce about the same amount of whole kernel. Funny enough, the hand cracking produced the most large pieces. So definitely an interaction between the type of cracker and cultivar. In terms of curing, that's a control treatment where the nuts are dried for 1 day ambient, under ambient airflow. For the various treatments then, there's a lot more treatments than these, but this is just to make the point. We expose the nuts to high temperatures for a brief period, so brief heat treatments between 5 and 40 minutes, in this instance at 50 degrees, followed by 35 degrees until moisture loss stopped. In a separate trial, we looked at covering the nuts with silica gel at ambient temperature. You're all aware of silica gel, what it is, what it does. Those little packets you sometimes find in packed food, it's a little white square with crystals in it. That's silica gel. It absorbs moisture extremely efficiently. Okay, so we took silica gel and covered the nuts to remove the moisture in that way. In the first trial, the heating one, where we gave the nuts that heat treatment, the whole kernel went from around 30% to just over 50%. Our assumption at that stage as to why this was happening, well, the most likely thing we thought was the heat was causing that shell to expand because hot objects expand, and that expansion of the shell away from the kernel broke contact between kernel and shell, so you didn't get an impact on the kernel when cracking. But the silica gel trials blew that out of the water because we didn't heat the shell in that instance. What we did notice though for both treatments is these treatments cause the shells to fracture, especially along the suture. So the current hypothesis is that by cracking it on the suture, we're giving the moisture in the kernel an escape route, that it doesn't involve passing through the shell, so it can leave a lot quicker. And possibly the rapid shrinkage of the kernel is allowing the kernel to pull away from the shell. So similar sort of mechanism, but in a different way. Discoloration. Okay. Discoloration of Beaumont in South Africa is a big issue. In the years when we did this work, and we're talking more than 10 years ago now, discoloration accounted for 20 to 25% of all our unsound kernel. In the last few years, that's dropped to between 7.7 and 13.9%, and probably the big difference between then and now is that our Beaumont has gone at that stage from 65% of the trees in the ground to around 43% of the trees in the ground. So gradually growers are moving away from the main culprit in the discoloration story. But at that stage it was important, so we did a bit of work. It was found by other researchers that the discoloration was caused by a water-soluble phenolic, and that's what it looks like. As you can see, that's a clean kernel. That's what we refer to in the industry as onion ring. It's a blemish around the equator, and that's basal discoloration. But those two issues seem to be related to each other in that when you look at them in comparison to the shell they're taken out of, the onion ring occurs where the nut is where the kernel is in contact with that dividing line between the white and the dark part of the shell. And indeed, if you look at the shell itself, you'll see the bleed of that, whatever that dark pigment is, it bleeds across into the white part of the shell. So we suspect that this phenomenon is due to a movement of that pigment from the shell to the kernel. Okay, one of the first things we found was that this particular order, most disorders increase with the season, but in this particular case, the order decreased through the season. So an easy solution at that stage was, well, harvest the Beaumonts later in the season, which growers were prone to do anyway. One of the other, or a couple of other things, as I said, it's a water-soluble phenolic. One of the other things we picked up is the affected kernel generally has more iron and manganese, and that told us possibly that the root cause of the disorder was the plant's roots, because that's where it gets its manganese and iron. And macadamias have proteoid roots, which have evolved over many millennia for the uptake of these sort of minerals. So the assumption was possibly we have a situation where those trees that are affected by discoloration have more proteoid roots. So one of the avenues we looked at was having an effect, or was to try and affect the proteoid root development. In these trials we did, that was by means of phosphorus applications and by means of growth inhibitors. We also had a look at calcium, because phenolics are always related to calcium status, especially in other foods. And we did some surveys at our processes to see if we were getting more discoloration in certain cultivars or in certain areas. And there was one interesting piece of data out of that, which I will show you. Okay, so the proteoid root development. Our rationale was giving the trees more phosphorus, because proteoid root development is driven by low phosphorus status. So we selected some bad orchards and applied some MKP to the soil. And in the second part of that trial, we applied uniconazole to the soil to inhibit root growth. Okay, so this was done at around flowering. And at harvest, this is the sort of results we've got. For the controls, okay, we rate the kernel at harvest on a scale of 0 to 4. 0, there's no discoloration. 4, it's extremely bad. So what we noticed immediately was, while the control treatments had a lot of the really bad discoloration, that pretty much disappeared with all treatments. And we also noted slight increases in the category 0 kernel, which is clean, and category 1 kernel, which is a thin onion ring. So that was looking promising. For the calcium trial, we looked at 5 products that are used as foliar applications. We sprayed 5 lines of trees, kept 2 control lines, a different product per line, and just had a look. This was in December. We commenced, and then weekly thereafter for 4 applications, and then had a look at the nuts at harvest. The only thing that really stood out here was this product, Calcimax, had a big drop in the category 3 kernel, which is sort of medium discoloration, and a slight increase in the category 0 and a decent increase in category 1. So it seems there is a role for calcium in this particular disorder, but again, we need a lot more work on that. The surveys I spoke about, not much came out of the data except for this. There is a strong correlation between total kernel recovery and onion ring. Whatever is driving thinner shells is the same process that's giving us discoloration. So that actually gives us a little clue as to where to go back and look at how to improve the kernel recovery, but no more about that today. It's something we're working on. Okay, so we've looked at visual things you can see easily, how much kernel there is, whether it's discolored, but there's a number of non-visual parameters that are extremely important. And these are the sort of things your processors measure. Peroxide value, free fatty acids, those are common measurements in the industries. And then some not so common ones for the processors is accelerated oxidation tests, and an acidine value, which looks more at secondary oxidation products. That's more relevant in kernel that's been stored for some time. It's not part of our trials, but just bear in mind the most important non-visual characteristic is taste, and that's the one your consumer will tell you about by buying other nuts. If you taste it in macadamia, just bear in mind macadamia being a small crop, there's lots of alternatives if you put out high peroxide values. Okay, so the industry standards at the moment for peroxide value, 3 milliequivalents, and free fatty acids 0.5%. I understand that's the same in Australia as in South Africa. The problem we had when we started this study was with those current standards, because those standards in South Africa are based on studies that were done in Hawaii in the 1960s. Different growing conditions, different cultivars, different processing methods. They only looked at kernels stored at ambient temperature. They didn't look at the effect of cooling the kernel after processing. They didn't take into account broken kernel. So those are the sort of factors we needed to understand if we were going to store our kernel more effectively. The other thing is our industry, or no industry, or no macadamia industry, has a standard test for setting sell-by dates. South African processors put it in a whatever, however many kilo bag, vacuum pack it, put it in a box and put a 1 year sell-by date on it. But what's that 1 year based on? I don't know. So that's something we thought we should have a look at as well. So there's 3 things I'm going to talk about: a baseline storage trial on how to store kernel and how long you can store it. The most recent study is the one we're busy with now, so I'll show you only the very first early data. That's where the fatty acid profiles affect kernel quality, and I'll tell you why we're looking at it later, and how can we predict shelf life. So the baseline study, we looked at the effect of harvesting time, early season, mid-season and late season kernel. Is this thing going in and out, or are you all hearing me? Okay. The effect of style, a broken versus the whole style, storage temperature, where the 4 temperatures were 25, 15, 5 and -5. The storage period between 0 and 24 months, and then after the vacuum pack bags come out of storage into retail packs and on the shelf for up to 20 weeks. And we had a look at peroxide value over that entire trial to see how it was changing. We also, at the start of the trial, took some of the initial nuts received and did an oxidation test on them, a enzymatic reduction time, just to see if that would give us an early indication of differences between the different types of style and season. So there's the 2 styles. There's the oxidation test, or the rapid oxidation test, the enzymatic induction test. This test tells us that for early season kernel, there's an induction time of 45 hours. That's pretty good. We heat the oil and monitor how quickly it breaks down. And if it takes 45 hours to produce volatile products, it means it's pretty good quality. The late season kernel, not so good. For style 5, 7.5 hours to get a oxidation, and style 1, 12 hours, 12.5 hours. So immediately we've seen that there are differences between harvesting times, and certainly later on in the season, differences between the styles. Okay, so for style 1, that's the results of the storage test or storage trial. What you'll see here is 3 columns. The one on the left is the early season, then the mid, then the late, and there's 4 rows. The top one is 25 degrees, followed by 15, 5 and -5. And on each individual chart, you will see there's a storage period ranging from 6 to 24 months, followed by a period on shelf of up to 20 weeks. What we note, the green plane there is the industry standard. You don't want to see values above the green level. So what we notice for style 1 is all the values at 15 degrees or lower are below the green plane. So 15 degrees is a good temperature to store style 1 for up to 2 years, but that's not the case when you move up to 25 degrees. Some of the early season stuff that was on the shelf for a long time started to show higher peroxide values, and that was more so the case for mid and late season. Picture is a little different for style 5, same setup, but different results. You'll see style 5 starts to break through the 3 milliequivalents for the early season kernel, funny enough, and if 1 or 2 places the late season is breaking through, even down the bottom there at -5 degrees. So the first recommendation then for style 5, you're going to need a lower storage temperature than 15 degrees, probably 5. The other important consideration is this difference between early, mid and late. And what confused us is why so many samples from the early season were of higher peroxide value than the mid-season. They were pretty much equivalent to the late season. My immediate hypothesis was we're getting some old nuts in the mix from the previous season. Possibly someone's been a bit careless about their cleanup, their pre-season cleanup. And so we had a look. We went to a couple of farms where they were tipping the first harvest into the bins, the trailers in the orchard, and we took samples, and we divided those samples into 3 according to what we saw. Freshly green nut husk, and in the worst case scenario, brown husks that are split. And that is obviously not from the most recent season's harvest. So immediately we know we're looking at a situation where the early season's batches are contaminated by leftovers from the previous season that weren't cleaned up. We did an oxidation test on these 3 types, and it confirmed that there were quality differences. Okay. What about the poor late season quality? Everybody looks at a nut on tree in June, July, and says, well, the husk is still green, it's hanging there nicely. Surely if we dehusk that, dry it, and pack it as quickly as the early season stuff, we should get roughly the same sort of quality. We don't. We've seen it in the previous trial. And our rationale is one of the things that might be affecting it is the ratio of unsaturated fatty acids in the kernel. Now, the unsaturated fatty acids are the ones that, the health-promoting fatty acids, the one we're all told to eat for heart health. Unfortunately, unsaturated fatty acids oxidize very readily, much more so than saturated fatty acids. And we thought maybe the ratios of the two is what was driving that late season poorer quality or poorer storage quality. So we started looking at that. That's the new work I spoke about. It's still in progress. We'll finish the end of this year, hopefully. But some of the early data for 816, wrong button. For 816, we see the ratio of unsaturated to saturated fatty acids definitely increases through the season. So definitely in June, there's a lot more unsaturated fatty acids than in February. So that sort of fits in with our theory. If you look at the individual fatty acids, that increase is primarily due to oleic acid. But the picture falls apart when you look at Beaumont. High levels of unsaturated fatty acids both in the start and the end of the season, but not so much in the middle. And that's not due to oleic acid, it's due to the formyloic acid. So quite considerable differences between the cultivars. What we also noticed in the course of this trial was when we took samples from various locations, Hazyview area, Nelspruit area, Barberton area, and at the coast, at Port Edward, we see differences in the amount of unsaturated fatty acids. These samples are all taken in the same week. So yes, there's very different, very definite regional differences. And from my cultivar trial, we took a range of cultivars, and again, we see even bigger differences here between 791, which goes up to a value of nearly 7, and say 816, as previously seen. So what does this mean for the future? Well, if the rest of the trial that we're doing is to show whether those nuts with high unsaturated levels oxidize more readily. That's what we're busy with. If we do show that, we might need to start considering packing individual cultivars, because once you mix them, you lose the benefits of some of the better cultivars. Okay, something else to bear in mind is some cultivars have much higher unsaturated fatty acid levels, which might be beneficial health-wise. So you might want to market the cultivars separately. Okay, last of all, shelf life. What we did in this trial, we looked at 2 parameters that were measured at kernel processing. The oxidation test and the peroxide value. We took samples from a range of processes over many of our growing areas. We did those 2 tests. We put it into storage for a year, and we had a look 1 year down the line how the peroxide value there compares to these 2 parameters. If there's a correlation, because if there is, that means we can use the early season peroxide value to predict in advance what the peroxide value will be in a year. There's a lot of graphs, but I'm just going to put the one up. And this shows us that for peroxide value measured at the start of the season, there's a very strong correlation with peroxide value measured in the same kernel stored for a year, 0.92. So that tells me that, yes, if I know the peroxide value at the start, I can probably predict what the peroxide value will be like in a year. Okay, I don't need 3, Lenny, I need just 1. Okay, so one of the other things that comes out of this is our starting peroxide values at the start. You will see, I told you earlier that the cutoff value is 3. You will see it ranged up until around 11 or 12. that tells me that our factories are either not doing the peroxide test, or they know they've got high peroxide and are marketing the kernel anyway. That's a bit worrying. But it ties in what some of the research here has shown about the peroxide values in your local markets. The other thing that's very important is when we look at a peroxide value of 3 at the start, if we look at what it's going to be like in a year's time, it's going to be around 15. So anything that's 3 now is great for export, but if you store it for a year at 15 degrees, it's not going to be suitable for export in a year. If you want 3 mil equivalents in a year's time, you're probably going to have to start off at around a half a mil equivalent when you pack. So we need to start rethinking our peroxide value standards. Okay, so to run through a few conclusions, yeah, the quality plays a significant role in South Africa in the income. The quality starts in the orchard. Cultivars play a big role. Research versus reality. You know, we do all this research, we come up with a value of 3, and the factories sell at 18 or 17 or whatever. So, yeah, there's not always a correlation between what the processors know and what they do. Well, certainly in South Africa, I'm not sure about, yeah. From some of the other trials, style 1 is much better than style 5 in terms of quality. Ambient temperature is not adequate. You can see that we've spoken about what is better. Mid-season kernel had the best quality overall in that particular trial. Fatty acid profiles, that's going to play a role in quality, I think. So we need to look at that in more detail. And peroxide value seems to be a good predictor, for style 5 at least, it seems to be a good predictor of future quality. It didn't quite work out for style 1, the correlations are not as good. Okay, and some acknowledgements, thank you.